What I want to do is, first of all, take care of any questions you have about the homework. I had students in my office, and I think I answered a couple questions about the problems that involve the triangle waveforms that were finite. We'll do those real quick. I'm not going to, I want you to just make sure you try really work these problems. Just getting the answer, knowing what the answer is not going to help you in things like the quiz or test. And that's the real key thing. And your general understanding. All right. What I want to do, I got a bunch of stuff to cover today. I want to go ahead and talk about the homework problems that you had. One of the problems was this simple one that I gave you the answer to. I believe the height of this was 1. I'm going to call this tau over 2, tau over 2. You can put a number in at the end. This is going to be my x of t here. X of t is actually equal to the triangle waveform I gave you. 1 minus, and this is 2 magnitude of t over tau times the pulse of tau of t. How many know what I'm talking about right here? That is the definition of the triangle waveform. The symbol we use for this is actually this. How many saw that symbol in the book? Anybody? It is in the solutions manual for sure if you have access to it. And if you need help with solutions or you need solutions, see me. I can't just put them out there because of one thing. It's copyright infringement. And now he's taping me. I might get sued for just saying that, but I'll help you get them. All right? And I'm for you guys.
I'll take that off.
I'm not doing this here, spending all this time with you to try to, I'm not doing this because I don't like you. I'm trying to get you to be good engineers. But this is the deal. You got to come see me if you need something. Now, if that's that, I gave you the transform, didn't I? I'm not going to work through this, but we can get it if we need to. We take a derivative of this, right? Then you get 2 pulses. You know the transform of the pulse, and they're time shifted, aren't they, class? So we can get that. Once we have that, if we want the integral of that, we simply do 1 over j omega t times x of j omega plus x of 0, the x of 0 from this one, times delta of omega, right? Do you remember this? Times 5. All right, I won't go there, but trust me, we can get that. So if we want this and we want the transform, this is what the quiz is going to be on. How I like it set up. And you'll do it too. I'll always have x of t over here, either an arrow or a straight line, and I want x of omega here. Now, this is x of t right here. Then this was tau over 2 times the sine of omega tau over 4 pi squared. How many remember seeing that, and how many got that one? No matter how you did it. Now, how many understand this? Hopefully everybody does. You got it. All right, we got that one, right? We always, when we look at functions, we always try to decompose them into functions we know that we can add. Because if you have x and y, x plus y is 2 functions of t, the transform of x plus y is just x of omega plus y of omega. Now, the next one was this. Now, if you saw me about this, and I told you how to do it, don't worry. I'm not going to call on you. But I want somebody else to just tell me, we know what this one is, don't we? This is a pulse. I'm going to do this one. If I have the pulse tau of t here, this goes to tau times the sine of omega tau over 2 pi. That one I told you need to know, right? Correct, class? Now, finally, based on those two, I put them there for a reason. I want this transform. I have x of t here, and I define it as a simple plot, and it looks like this. By the way, for this one right here, what was tau? And this one, what was the total spread that I gave you?
2.
It was 2. So this value was 1, tau was 2, and you can make the appropriate changes here. Yes?
I'm pretty sure in these you gave us x of omega and had us find the inverse.
All right, we can do it either way.
Yeah.
It's fine. We'll do that, though. I'm sorry, you're right about that. I looked at these before I came down. I gave you x of omega looks like this. We'll go ahead and do it. Item 1, right? First, I want to create the functional form of this. Now, when I look at this, really, it's irrelevant if this is time or omega, right, as far as the form of this function. Not the transform, but the form. So, if we wanted to build this, do you agree that this right here could be represented as, this is omega, and this is 1 here. This could be represented as simply a square pulse of height 1, where this would be tau over 2 minus tau over 2, minus, and it would be a simple triangle. It would be minus this, though. This would be tau over 2 minus tau over 2 and tau over 2 with height 1. Y'all agree with that? Okay. I'll write the mathematics of this. A lot of people sometimes fall on the face here because mathematically they don't know what functions look like, and if they see a function, they can't mathematically describe it. And I promise you that is a problem for engineers. They're not used to doing that. That's the reason. Once you get used to doing it, the problem goes away. So for this one, how do you describe it? Not you guys. Somebody else. In the back here, how do you describe it? Anyone? Back of the room. Kim, how do you describe it? How do you describe this one? You've seen it a few times. Let's resume this.
A pulse.
All right, go ahead. It's going to be a pulse of what's the width? Tau. All right. Of omega, right? Now, the actual value of tau there was 2 pi, I believe, wasn't it? Take a look. I went from minus pi to plus pi, didn't it? We can go ahead and put that in. We don't have to. Is it minus 1 to 1?
Yeah.
I'm sorry. Minus 1 to 1. Well, in that case, then tau here is 2, isn't it? Or 2. Tau, if it's minus 1 to 1, tau is 2. Tau is 2. You got to keep me straight on this. Do you agree with this, class? So this would be just 2 here, if you wanted it. What about this one? Now, this one would be a triangle, right? This one's a little more work, but it's still the same form. Mathematically, this one is going to be 1 minus 2 magnitude of omega divided by the width of tau, right, times the pulse of tau of omega. Do you agree? Let's go ahead and put in the actual real value. That was minus a half to plus a half, is that right? Take a look. Minus 1 to 1. Is this minus 1 to 1 too, right? Okay, so this is the same. I'm sorry about this. So tau is equal to 2. If tau is equal to 2, that goes away, and that goes to 2. Do you agree? Maybe a lot of you see this, but I want to make sure everybody does. Now, if I've got that, and I want to take the transform, I want to go to the time domain. Now I want the inverse transform of this. Here's where we can invoke duality if we want. I think we've done this before, though. Here, you know, we take that and replace omega by t, right? We did this one last time. So we have tau sinc of t, tau over 2 pi. It goes to, and this is going to be 2 pi over here, right? And then over here it becomes p tau of minus omega, technically, right? Isn't p of minus omega the same thing as p of omega? Because if you just flip that function around the origin, it's the same. So I'm just going to leave it as p of omega here. And you can see what else then. That this p tau of omega is equal to this divided by 2 pi. Do we agree? Now this is what we want, don't we? So the inverse transform of this is going to be this. Do we agree? Going to the time domain. Does everybody see this, by the way? You understand the logic of this? All right. You may remember this transform, but I don't think you do, and I want to make sure you understand how to get there. The minute you have duality going for you, and you know about 3 or 4 basic transform pairs, you can get them all. All of them. So now I come here, and I go ahead and get it. What does this become? Oh, sorry. I didn't do the pulse. Well, what is that? I did the pulse, yeah. What does this become, guys? Well, I have it, right? Tau is what? 2, correct? This is 2, so this becomes, that's going to be equal to 1 over pi, it looks like. 1 over pi times the sink of what? Class? T over pi, isn't it? Do we agree with that? Follow my thoughts on this one. I could have made, nice numbers and stuff if I put it from minus pi to pi, but that's okay. What about this one? What happens here? We invoke duality again. I'll just tell you a trick with this. I know if I go time to omega, and I have the form of the function in the omega domain, when I go back to time, I divide by 2 pi. I mean, in other words, when I take this over here, and I want what it is over here for omega, I divide it by 2 pi. Now, if you've been working this, you see it too. If you don't, just go through duality again. And if I do, what happens? I take this over here, correct? Replace omega with t. And I take this over here, multiply by 2 pi, right? So I'll have the triangle function, right, times 2 pi, argument of minus omega. Is the triangle function of minus omega the same as the triangle function of omega, class? In your own words, why is that so? You can flip it and it looks the same. Literally spin it around the origin, doesn't it? Now you can't do that with u of t. That doesn't work. And it doesn't work for an exponential decay times u of t. But anything that is perfectly symmetric about the vertical axis at 0 that flips like that, the function of omega is equal to the function of minus omega, or the function of t is equal to the function of minus t. Are we good? So what does this one become? That's the triangle, right? Maybe I should just do this. I'll leave it as triangle tau of omega. When we go back, a triangle becomes what? Come on. Tau over 2, right? Times the sink squared of what? Come on. It's going to be not omega anymore. We went from omega, we're in what domain? T. So it's going to be what?
T tau over 4.
T times the tau over 4 pi, right? But when we have to do one more thing. We're almost there. What do we have to do? Divide by 2 pi, correct? So when we divide this by 2 pi, it looks like this. Correct, class? And there's one last thing, and that's why I circled this. Somebody had a discussion with me about negative signs. Is that you? I don't know. Somebody did, and I said, yeah, they're bad with me too. I miss them all the time. I circled. I talked to somebody in this class. Was it you, Al? It's one of the things that I recommend doing because I'm bad. My eyes are getting red. And as I go through a proof, anytime there's a minus sign, I circle it, so don't forget to carry it down. Because sometimes my handwriting is horrible. A minus looks like just an accidental scratch. Do it. Now there's a minus sign here. Got it? That's what the transform is. I want you to just ask yourself this too. What is the value of a sinc function with the argument of 0? What is sinc of 0? 1. Now think about the way a sinc function looks. If this is the argument, I'm going to just say sinc here of t. It looks like this. The height is 1. When it's 0 here, if this is time, the value is 1. Now, just work with me here and I'll show you what I'm doing. I have 1 divided by pi here, right? What do I have here? Well, that's going to be 1 as well. 1 squared still is 1. Right? But now I'm dividing by tau, which is 2, right? Over 2, correct? So I'll get rid of this, but I have 2 pi here, right? So if I have 1 over pi minus 1 over 2 pi, I have 1 over 2 pi, don't I? Think about it. So that would be, at t equals 0, that's what it would be if I asked you to evaluate. Trust me, if you think about what I'm saying, it'll make sense. I'm just evaluating 2 functions and subtracting them. What this would look like, though, is something where this is changing faster than this. And as t gets large, this one would dominate. But I'm telling you it's a little advanced. Just telling you. All right, that's how you do that one. Was there another question you had? Yeah.
3b.
What is it?
Find, you're given the transform of omega.
to be 1 over A plus J omega, and you want to find X of 5T
Okay.
minus 4.
This is actually, that's a good problem. I think that problem's in your book, but I'm not sure. Did anybody see that in your book or not? I don't know. I thought it was. All right, we have the x of t here goes to x of omega business. This is the way I like doing it. Now, give me what x of omega is over here.
1 over A plus J omega.
I'm surprised you asked me that one. I think you know this one. How many know this? What is it, guys? It's one you have to know.
Negative 8.
It's e to the minus at times u of t. You got to know that one. I mean, you just got to know the transform pair. You can't survive in engineering. Promise you, you got to know these transform pairs. The pulse to sink, the exponential decay times u of t to that, the e to the minus a magnitude of t to the 2a over omega squared plus a squared. What happens when you take x of t times cosine, sine, or e to the j omega naught t? Those you got to know. That's modulation. Big deal to me, big deal to you. You'll see. Now, if I have that, what's the first thing I want to know?
I found X of T minus 4 over 5.
Oh, but let's do it. What is x of? Go ahead.
You want 5T minus 4.
All right, here's what we're going to do. Before I do that one, I want to break it up into something where I have just x of at, all right? And I'll show you what. I'm going to take this. Isn't this really like x of 5 times the quantity t minus 4/5? Do you agree with me, class? Think about what I'm going for. I'm working here on 2 levels. I know that x of at will transform as 1 over the magnitude of a, capital X of omega over a. And I'm going to just say for a greater than 0 for now and assume it's real. I don't want to start playing around with imaginary values of a. Now, if I have that, I know I've got 5 times this, right? And then I think about the tangling property. X of t minus a constant c goes to what? Now, you tell me this one, because you guys know this. You know you're getting a quiz on this stuff. What is it?
X of omega.
It's e. It's what?
X of omega.
X of omega. One at a time. You asked it. What is it?
E to the minus J omega C.
E to the minus j omega c. Is that right, guys? How many agree with it? All right, we have that. We want to match those properties, right? So what we do is we look here. I don't want x of 5 t minus 4/5. What I want to know is what does x of 5t go to first? You'll see where I'm going with this, right? Well, what does that go to? I got my x of t, don't I?
Right.
So what does it become? It's going to be 1 over 5 times 1 over a plus j omega over 5, isn't it?
Why can't you do X of T minus 4/5 first?
I'm not done. I could. Just let me do this one first, okay? Are you with me? Now what I do is I say this function looks like the function I want. I'll call this x prime for now. Then I say it doesn't need a derivative. Now I'm going to say my real x of t is this. You understand what I'm going here? I said I had an old x of t. I didn't like it. It didn't fit the form. This is my new x of t that I happen to know the transform of. Got it? This x of t, which is my old x of 5t, goes to this. Now what am I going to do? You're having with that. I'm going to go ahead and say this is really, I don't want that. I want the x of the new t, but I want it minus 4/5, don't I? Look here. See what I'm doing here? And what does that become? Isn't that just time shifting again? And you told me what it is right here, right? What does it go to? E to the minus, come on. It's going to be e to the minus j omega, but really 4/5 times that, right? So I'll put e to the minus j 4/5 of omega times, or divided by 5, times 1 over, now a in this case was what, 5, wasn't it? Or excuse me, what was it in the beginning?
It's 5.
this A? Did it have any value?
It was never defined. It was just that's
Okay,
the.
we'll leave it as A then. All right? I mean, it wasn't, right? It was just left as A always?
Yeah. For that, and then all the other ones were just given.
Well, the other numbers were given, but
Yeah.
that one wasn't. So that's general, so it's going to stick there, right? Got me? What's the next one you want? I bet you can see me.
That was it.
All right, I got one for you. What if I asked this? Not you, and not Caleb, and not Alec, and not Kumar, not you. Somebody in this row besides Alec and you. There's three of you. I want to know what this is. Suppose I give you x of t. Look at me and think about this first. And I want to know what it is for the transform of dx of t. Don't answer dt. Now what it is. Assuming I know this pair, back here, guys, this row. What is that? You said it. It's going to be j omega times x of omega, because I know whenever I have a time derivative, if I know x of t goes to x of omega, if I take the derivative of x of t, and I want to know what that transform is, what it looks like in the frequency domain, I just multiply by j omega. You're right. Okay? With me? What about this? Not hard. What if I take this, x of t times cosine of 6t, and I want to know what the transform of that is? I'm not doing a lot of erasing because I want to cover the ground today. Now, somebody else besides the usual suspects, tell me what that is. Not you, Demetrius. How about, you know what you're doing, what is that going to be? What property are we invoking here? Think about it, the ones I scream about.
1/2.
Well, what property though?
Multiply on cosine.
Hold on. What? It's modulation.
Yeah, modulation.
All right, now I'm not trying to intimidate you. I'm trying, this will help you remember, I promise you. If I work with you here, it'll stick. All right? You know it, go ahead, say it.
1/2 capital X of 6 minus omega naught, or 6 plus omega naught.
Let's do it, omega plus 6, that's what I like to see.
Okay.
Go ahead.
Plus omega naught 6.
Is he right, class? Instead of x of that, what do I replace that with? That. And it's then what it would be. It would be 1 over a plus j quantity omega plus 6 plus 1 over a j omega minus 6 and the 1/2 out in front. Are we good with that? What if it was a sign here? You don't have to write this down. What if it was a sign? We almost got it. I'll leave that form, but we're not quite there. Now, somebody else. Hold on. How about this row? Not you, Kim, not you, Dimitri. This row here. You want it there back in the back or not? Come on, sine. You know sine. It's a joke, isn't it? X of t times sine of t. Do you know what it goes to? Who can help them?
Is it J over J?
It's going to be j over 2 instead of just 1/2, right? It's j over 2. We're almost there. Not that, it's that, but what happens here? Minus. Got to know that one too, guys. Got to know that one, right? Now, you answer, he knows this one, but if I just took this times e to the j 6t, now, ignore that. Where does that go to? You just told me a second ago. I think you gave it, wasn't that right here?
Yep.
Well, no, actually it isn't.
Oh, no.
I'm sorry, you could use duality to go there, but never mind. I'm sorry. I won't give you duality. Go ahead, look it up. I want you to remember this one. So
Duality?
No, don't use duality. Just look. This is multiplying by a simple complex exponential.
Omega minus omega naught 6.
It's x of omega
6.
minus 6. This is the one without the divide by 2 business. You just find out what x of omega is and subtract 6. You can get it from duality here, but I don't want to go there. Okay? Now, Are there any other questions about that homework? Because I think I'm showing you the properties there's a few other properties, right? We could do convolution of the time domain. It's just multiplying the two functions, transforms in the frequency domain, big with engineers, right? We saw duality. I think we're good to go here. Any other thing you want looked at? Because I can draw the x of omega or the x of t. You'd have to describe it with a function. And then you would have to get the inverse transform, right? I think you're good. Now I want to spend a little time talking about some important issues. A few things that I want to just put to the rest right here. Put the rest right here. Things that are important. Is this helping what I'm doing or not, class? Just let me know. I have no idea sometimes if it is or isn't, and that's the reason I ask. I get some blank looks sometimes, and I don't know. Did I say something you didn't understand? You feeling you're getting this, guys? I hope so. Now this one is important, more so because it'll make you understand what's real and what isn't. Think about that for a second. Now watch. And write this down. In general, x of t here, x of omega here, h of t here, h of omega here. Output of the system is described by y of t equals x of t convolved with h of t, or y of omega is x of omega times h of omega. The general form of systems. We could describe them with differential equations. I like block diagrams. Engineers use block diagrams. We have this here. And now we're going to talk about a few things you have to be aware of. Now, what if I said that I had a system where I have a delta of t going into it? And this is what happens a lot of times when you look at the way problems are presented. That's a time domain function, right? But the property of h of omega here is given not in the time domain, but in the frequency domain. And it shows you something like this. All right? And they want to know what the output is here. Now, how would you approach that problem? Just tell me. Most of you know what you're doing. You got a good feel for it. We like to work in the frequency domain, don't we? Can we get this into the frequency domain? What is it? 1. It's just 1, right? So in the frequency domain, this thing is 1. How do I get the output, y of omega then? What do I do? I take h, which is here, times this, don't I? What does this look like to you? Pulse. Pulse times 1 is a pulse. So, in fact, I'll show you something here. This would be equal to simply a pulse function of width tau of omega, correct? The output. Now, when did the input actually take place? T equals 0, right? I'm going to show you something that should make you, it should bother you. What does the time domain function of this look like? Think about it. It's going to be a sinc, right? What's a sinc of? Of tau over 2 pi, isn't it? Take a look. Isn't this going to be tau over 2 pi times the sinc, right? Now it's going to be t times tau over 2 pi, right? Now most of you are already seeing it, I think. Do you agree with this, class? I think that transform's actually in your book. I think they give you P of omega goes through this. Check. I don't know if it is, to tell you the truth, because I don't use those things. All right. Now, if you see this, I want you to think about it. The input versus time was a delta function, right? That was my x of t. The output versus time is a sinc function. Most of you can see this, right? That's the output, that's the input. Well, guess what? Before the input ever occurred, I have the output. Think about it. T equals minus 7 seconds. We still haven't hit 0, right? If we are in the real world, it says if I hit this system with an impulse, it knows at the 7 seconds before 0 that we have an output. Matter of fact, it has an output for all time before 0. It anticipates the input. Now, I'll level with you. That's non-causal. A causal system means something caused the output after the input occurred. And it makes sense to you. All real systems don't have some sort of, I don't know, fourth dimensional property or something like that. They're futuristic and can't see things in the time domain for all time. They can't anticipate inputs. And the truth is, you cannot build this filter. You can't make a filter that absolutely prevents any frequencies here and here in the domain of real time. In other words, in the environment. If you try to build this with parts, you can't. You can get close, but you can't build it. Now here's the thing though. If I record data, say I record data for a very long period of time, then a filter like this will work, an ideal filter. You can do that. But the thing about it is this. It already knows all the values up and down the strip chart axis of time. In other words, it's recorded everything. So it's not anymore anticipating an input. It knows what the input is for all time. Now, when they have recorded data, then you can use a filter like that. Actually, I don't know what they use in the audio world, because it's all digital signal processing. But you can use all these filters that you can't realize in the time domain that we live in. Okay, class? Now that's an important property. It seems silly. How many understand what I'm getting at here? You're seeing an output occur here long before the input happened. That ain't happening in my world. It just doesn't happen. It's a lot of football players who wish that happened. Because then we could get touchdowns before we even hit the field. That ain't going to happen. Now, that's the first thing I want to tell you. The second thing is you've noticed that we have just stuck with the e to the j n omega naught t, if we're in a periodic domain, times some constants. We assemble functions using linear combinations. Magnitude, say we get like the DC component, say 1 plus 5 e to the j 6t plus maybe 10 e to the j 20t plus we keep going on and we assemble a function in terms of exponentials using Fourier series analysis if it's periodic in time. Do you agree, class? And if it's not something periodic, we use a Fourier transform to describe that function x of omega. And we can if we have an x of omega that we happen to like, we can get the x of t. We can synthesize it. Do you agree, class? But we still have the fundamental kernel that appears there, the e to the j omega naught or j omega t, correct? Here's something interesting about that. Those are called eigenfunctions, and here's why. And I'll do it over here. This you don't have to write down, but I want you to appreciate it. If I have this, I'm going to do this in the time domain, and I have h of t. I'm going to put in the first term or a term of a Fourier series. I'm going to just say I have e to the j omega t times some constant a here. Doesn't matter if it's a, b, c, and it goes in. Now, what comes out? What we're supposed to do if we're in this time domain is convolve them, right? I want you to just watch this. You don't have to do this, just watch. Now my output here, my y of t, will be equal to the integral from minus t, from minus infinity to infinity. I won't shift that one. I'll call it h of lambda. You remember convolution. T becomes lambda. This one, I'm not going to do any flipping on. Then I take that and I flip it. So I get e to the j and omega. Now it's t minus lambda, d lambda. Do you agree with that? Trust me, it's the definition of convolution. This is the one we shift with respect to t minus lambda. Now watch, and don't do anything here. Can't I take this e to the j omega t out in front? Right here? Do you agree? And can't I just make this, where that exponential was, e to the minus j omega lambda right there. Now take a careful look at that. Something should go off in your head. What is this? Think about it. If h of t was known, what is that? It's the Fourier transform of h of t, isn't it? Because instead of lambda, if I put time there, it doesn't matter. I'm integrating through that. I have the Fourier transform of that. Do you see this, class? So that means my y of t here is really equal to e to the j omega t times h of omega. Now, here's the big deal. Do you see this e to the j omega t? It appears here, and it appears out there. The a here, actually, I should have put an a in here. I'm sorry. Would appear here as well. It's just the input times h of omega, evaluated at h of omega. It's called an eigenfunction. It's a unique function, singular function. The actual time domain form of that function appears in the output. So every single frequency that you have in the input frequency will appear in the output or be zero. In other words, if the h of omega was zero at that frequency, and if it isn't zero, everything appears. Every input frequency appears in the output if it's a linear time invariant system, okay? That's important. One more thing I'm going to do here. Now, you don't see the importance of that yet, but you will, because that should make you understand why we've got such a thing for this e to the j omega t operator. Because we can analyze stuff in the time or frequency domain and simply get these unique transforms, this h of omega, which is really the transfer function to describe the output for all input. Should have probably said that earlier. Now, you remember I talked about the sampling business, right? And somebody asked me about one of the problems I gave you. I'm going to just, I don't remember the numbers, but if I had x of t is equal to cosine of 40t, plus the sine of 20t, right? And I want to know how fast I have to sample that so there is no aliasing. That's the bottom line. Now tell me how I would do that. Anybody this time?
Twice the highest frequency.
What is the highest frequency? 40. Why? Because you're not dumb. Because that's one omega naught there, and there's another omega naught there. I'll call this omega 1, call this omega 2, right? And I can see that 40 is larger than 20. It's as good as it gets, right? Now what do? Keep going. I want the sampling period. We've got omega naught. How do I get f? How do I get f? Come on, help him. What is omega in terms of f? 2 pi f, you're engineers. So what is f? 20 over pi, is it? Guys? Did I do that right? I hope so. Now, if that's f, what is the period?
Pi over 20.
1 over f, right? It's 1 over f naught. It's equal to pi over 20, right? That means I have to sample with intervals no larger than that if I want to prevent aliasing. Now, excuse me, twice that. That's the actual frequency. I have to sample it twice that. So the actual value of Ts, the sampling frequency, would be 1 over 2 f naught, or it would be equal to pi over 40. I'm sorry about that. You with me on this, class? The relationship between frequency and period, always twice the highest frequency of interest, or 1/2 a period. Okay? I just said that. Make sure you understand this. Yes, you're going to get your quiz now. Why don't you do yourself a favor? Put your books away and take out one blank sheet of paper in case you're going to do scratch work. You shouldn't have to, but in case you need it. One blank piece of paper. As soon as everything's on the floor, I'll give you the quiz. Honestly, did this help at all, guys? Just give me a show of hands if it did. I need to know.
What?
If this lecture helped your understanding, because I need to know.
Yeah.
I don't see a lot of you in my office lately. I see the usual suspects, 2, 3, Kumon. I haven't seen you or you lately, or you.
You have any?
All right, ready?